Hey, welcome back. My name is Jordan Deshawn, and in this video, we're going to be covering step 4, which is about pumping. And the main question to address here is what pump and power requirements are needed to achieve the desired performance. So under step 4A, we answer this first question: what type of pump is being used? And there's a few to select from this drop-down list. There's a solar pump, an AC centrifugal pump, and an AC centrifugal pump with inverter. For this design example, we're going to select a solar pump. And we can see here the design engineer is selecting a Grundfos pump with the pump model SQF5-70. So that's an SQ Flex pump, which is a solar pump. But you might be wondering, how do we select a certain model of solar pump? What we need to do is ensure that we select the pump that can achieve the desired performance. And that's based on the results from step 3. We have a specific design flow rate and total dynamic head that we need our pump to operate at. So that's a flow rate of 5.6 cubic meters per hour and a head of 75.3 meters. Let's look on the Grundfos website to find a pump that's appropriate for that. And again, you can change your location here. Let's say that we're doing this project in Indonesia. You can come to the Grundfos Indonesia website. You can see that here by this ID, and then search for a product. In this case, the SQ Flex. And we can click on this first one, the SQ Flex. If we scroll down, we can then click here on the product page, which will take us to a place where we can see all the different models of this pump variety. So we can see here a list of various product numbers, product names, and different characteristics of the pump of interest. So for each pump, it's important to check out the rated DC voltage, the range that goes here from 30 to 300, the phase of the pump, and probably the most important thing is to look at the pump curve. So you can see if I hover my mouse over the pump curve here, we can see on the y-axis it shows the flow range. And then the blue lines with numbers labeled 80, 90, 100, 110 within the pump curve show the different TDH values. So our goal in looking at the pump curve is to see if there's a pump that can accommodate our flow range. And I think we'll need to go to the second page here to find that pump. So continuing to hover over, if you remember, our flow is 5.6 cubic meters per hour. So the upper limit of this pump curve is 5 cubic meters per hour, so it doesn't quite reach it. But looking at this next one, the flow goes all the way up to 8 cubic meters per hour here. So this one looks like it could be acceptable. Our flow was 5.6 cubic meters per hour, and our head was about 75 meters. So if we look at the y-axis, actually let's just click into this pump to see it closer up. Here under the curves, we can see we have a flow of about 5.6, and what we'll do is read over until it intersects with our TDH value, which is about 75, which seems to occur right about there, but a little bit lower. Let's see if I can get it to go there. Oh, it looks like I can change the input here. See if I enter. Okay, there we go. So if I've entered the input here, a flow of 5.6 cubic meters per hour and a head of 75.3 meters, we can see that it does fall on this pump curve. And we can see the P1 power requirement is 2.45 kilowatts. So this pump model is of the higher 2.5 kilowatt variety SQ Flex comes in. So, and then this is the model that was selected by the design engineer, SQF5-70. We can click on the specifications tab to read more about this pump, to see the rated DC voltage range, the rated current, and the power input. And that's what we enter here at the top of step 4. You can see it's a single phase pump. The frequency can either operate at 50 or 60 hertz. That's applicable to the SQ Flex pumps. The rated power is 2.5 kilowatts. There's a rated AC voltage, 9 to 240. A rated current of 12.5 amps, and then this is the range of the DC voltage, 100 to 300. You also get the motor power at the duty point, 2.35 kilowatts. That's about what our results were showing. And then we have the pump curve. So in these two columns, these are for user input. We're going to enter different flows from the lowest all the way up to the highest. And you can see we get a little bit more granular as we get higher up. And then the power P1 requirements along that pump curve for a given or fixed system head equal to our TDH. So to do this, we'll have to look at the pump curve and find the flow and see where that intersects our pump curve. So with a TDH of about 75.3, that falls around this line in between the 60 and 80 TDH lines. So starting at 0, we'll read over and find that power P1, which is about 0.9 kilowatts. So that occurred right about here. And then reading up at 1 cubic meter per hour, we can read over to the 75 mark, and it looks like that's a power of about 1 kilowatt. Let's see what was entered. 1, exactly. Next, we'll look at 2 cubic meters per hour, and again, we'll see where that intersects with the TDH line of 75. 2 reading over to 75. Looks like that's at about 1.2 kilowatts. And you can see we just continue on doing this for all the different flow inputs. Again, it's up to you. Your job is to just enter 10 points for flow and motor power from the manufacturer's pump curve. And then we can see from this, we get that pump curve that's replicated here. It goes up almost to 2.5 kilowatts, and it's for these various flows all the way up to 5.8. So that's how we enter a solar pump curve information here. If desired, you could enter treatment loss information, but that's optional. You can click on this optional calculators link to get what that treatment loss information would be. Next, in step 4B, we do a few pump checks. We enter the pump casing. That's the inner diameter casing for the borehole, and then the maximum diameter of the pump. And you can see from these two values, there's a pretty significant difference. The borehole casing is much wider than the pump diameter. What this means is it might be necessary to use a pump sleeve to achieve better pump cooling. So we can see here the design engineer has entered an inner diameter of the borehole casing or pump sleeve. These two values are different, indicating that there will be a pump sleeve used. And then that achieves a minimum cooling flow rate of 2. So that means this is the lowest speed that the pump should be operating at, is 2 cubic meters per hour. Next is step 4C, which is about power source checks. But in this case, we're just using solar, and so we can just use step 5 to check if the solar is sufficient. Step 4D is for inverter selection, but that's not applicable since we're using just a solar pump. And finally, we get a summary of step 4, which gives us the type of pump, the pump model, and the model number, or the model name, the motor power at duty point, and then the power source, which is solar. And then in this case, we're not using an inverter, so those are not applicable, or NA. So that's the end of step 4. Next, we're going to be looking at step 5, which is solar. So stick around and check out that video.